Okay, we'll go ahead and get started right now. Okay, hello everyone. Welcome to the webinar today. My name is David Din. I'm a sales engineer with JuliaHub. And today we're going to be doing a webinar as part of our Julia for Engineers learning series. And we're going to show you how you can create acausal components with Dyad today. The intention of today is to sort of be a step-by-step lesson. So whether you do it right now or you follow along on the watching the recording of this, you should be able to see every single step that I take to create the component library that we're about to show you today. So step-by-step tutorial is the intention here. All right. So with that, we'll go ahead and get started. Here's the agenda for today. I'm going to do a very brief overview of the Julia programming language. For those of you who are not familiar, we'll do a quick overview of what Dyad is, and then we'll get into the meat of today's presentation right away, which is how we can design an RLC circuit and analyze that model in Julia and Dyad. in Dyad. Okay, so we here at JuliaHub have worked with many companies and programs across various industries, such as aerospace, automotive, robotics, and AI. And all of these companies face the same problem, which we call the two culture or the two language problem. So if you think about the life cycle and the development of any given program or project, you have the earlier stages of a life cycle, and then you have the later stages of the program life cycle where things are about to go into production and development. So the idea is earlier on in the life cycle, researchers, engineers, and scientists generally prefer higher level succinct programming languages that allow them to perform research and analysis without having to worry about things like low level memory management and programming details and optimization. And ultimately, this leads this group of users to languages such as Python, MATLAB, and so on. Developers, on the other hand, they require scalability and performance in their production environments. And ultimately, this leads the developers to using languages such as C, C++, Java, and so on. So you can see here, as we transition from the earlier stages of a program to the latter stages, all the framework, models, and work that was done by the engineers must be rewritten in a language that's suitable for deployment. And ultimately, what this does is it leads to refactoring of models, friction in production, and obviously, in many ways, redundant work. So Julia solves this two-language problem by combining the ease of use and expressive syntax of high-level languages such as Python with the speed of low-level languages such as C and Fortran. Modern language design and compiler techniques have made it possible to provide a single environment productive enough for prototyping, yet efficient enough for deploying performance-intensive applications. And of course, these statements are supported by both open source and domain-specific benchmarks. So if we look on the left side right over here, we have data and results from the Computer Language Benchmark Game program. This is an open source project which aims to compare how a given subset of algorithms can be implemented in various programming languages that you see right here. So we can see here in this graph that Julia occupies the lower left-hand corner in which the execution time is low. In other words, the algorithms execute fast. And also the compressed code size is also low, meaning the number of lines of Julia code required to implement any given algorithm is low relative to its peers. On the right side over here, we have a domain-specific benchmark. We have a rigid body system represented as a non-stiff ordinary differential equation. And we can see the Julia implementation in green being compared with a few other implementations in different frameworks, Fortran, Sundials, MATLAB, and the Solve. You can see here that for any given acceptable error level in the solution, the Julia solution converges anywhere from 1 to 2 orders of magnitude faster than its competitors. Okay, so that's what Julia is. And so what is scientific machine learning or SciML? A lot of you who've heard of the Julia ecosystem before, have probably also heard of this SciML or scientific machine learning. So the idea behind SciML, it is an ecosystem of open source packages designed for machine learning, and they're all implemented in Julia. So the tools in the SciML ecosystem are designed for combining machine learning with traditional numeric methods, such as differential equations, optimization, probabilistic programming, and so on. So the idea is that data gives us insights from the real world, whereas models brings us the power of scientific principles, right? The physical laws which we understand that our world abides by. The idea is when you combine the data and the models, you get the best of both worlds. Accurate, interpretable, and predictive solutions that learn from experience while staying grounded in reality. And of course, because SciML is written in Julia, it is fully open source and also benefits from the composability, speed, and ease of use that Julia also does. Okay, so while both Julia and SciML are fully open source, we here at JuliaHub are building out an ecosystem for enterprises to adopt scientific machine learning as well as Julia. And at the center of this ecosystem is Dyad, which is our modern modeling and simulation framework powered by machine learning. Dyad is built on open source components, specifically, of course, the SciML ecosystem and Julia. In Dyad, we provide model development support in the form of visual drag and drop GUIs as well as IDEs for coding. We'll be spending our time here today in the IDE. We also have our AI capabilities, allowing for model refinement and analysis, allowing us to bring data into models, calibrate models, discovering physics, as well as optimization and control. And of course, we follow various model deployment standards, including FMU generation, CI/CD pipelines, and we've also built out some domain or industry-specific libraries for our partners to use. So we'll be spending a little bit of time today, or most of our time today, using the Dyad language. So the Dyad language here is a declarative programming language purpose-built for physical and hardware system modeling. Dyad models have a one-to-one mapping between code base and visual GUI representations. Okay, and what that does is it enables different sets of users to work on a single source of truth, right? If you think about many organizations, often they have multiple groups split up in sometimes maybe engineering and software development. Engineers generally prefer working with schematics, desktop or web-based GUIs, manual workflows, and they're very familiar with the system engineering beat. Software engineers, on the other hand, prefer working with source code, IDEs, CI/CD pipelines, and as well as software development lifecycle and agile methodologies. So Dyad models and the Dyad language enables these different types of users to work on a single source of truth because Dyad models, again, have a one-to-one mapping between both code base and visual GUI representations. And also, of course, it has tight integration with the Julia and SciML ecosystem. Okay, so just as to illustrate just a little bit, here's a simple solar panel model implemented on Dyad on the left side. Here we have a declaration for this simple solar panel model. You can see that it has a few variables for this model, irradiance, temperature, and so on. It has some parameters, which are like the knowns of this model, as well as equations or physical relationships that dictate the physics of this model, right? We have equations calculating temperature, irradiance, efficiency, and power throughout the solar panel. So what happens is we will implement our models in Dyad, and the Dyad compiler will generate the Julia code or the modeling toolkit model underneath the hood for us automatically. So this right here, what you see on the right side is Julia code using a package from the SciML ecosystem, specifically modeling toolkit. And this is the generated model that comes from our Dyad model that you see on the left side. Okay, so you don't really have to worry about too much about what's going on here. The idea is that you just need to implement the more intuitive model on the left side, and the model on the right side is what gets generated for you. And this is what we mean by one-to-one mapping between Dyad and the code base interface. And you'll see this today throughout the tutorial as well. So that's the one-to-one mapping between the Dyad and also the code base interface. Here's another example of a more complex model. Here on the left side, we have a active suspension model implemented in Dyad. This model is simply a vehicle that's moving over a road. right? So here you can see there's a wheel as well as the car and the seat that represents the vehicle moving over the road. We also have the road itself as well as like a PID controller in the loop. And on the right side, this is the visual representation of the same model inside our GUI called Dyad Builder. And you can see here it has the same thing, right? We have the seat, the car suspension, and the wheel. We have the road and the road data, and also the PID controller in the loop right here, controlling the response of the vehicle as it moves over the road. Okay, so just kind of give you a quick preview of what we mean by both one-to-one mapping between diet and code, and also the one-to-one mapping between diet and visual representations. And we have webinars available showing us manipulating this model like this, both from the GUI and the web-based or the code-based interface. So if you want to see that in action, either look on our webinars at juliahub.com or just ask and I can send you guys a link. Um, yeah, okay, so that's enough for the preview. That's what Julia is, what SciML is, and also what Dyad is, okay? So now let's go ahead and get into a hands-on example so all of this becomes a lot clearer. So for today, the problem we're going to take for this lesson will be designing an RLC circuit in Dyad and simulating this circuit with a voltage source, right? So basically what we're gonna do is we're gonna go in and we're gonna design a capacitor, a resistor, inductor, a voltage source, as well as a ground. And then what we're gonna do is we're gonna stitch all of these together into one RLC model, and then we'll provide a voltage signal to this source, and we'll see the responses throughout our system. Okay? So with that, I'm going to go ahead and move this to the right side over here. I'm going to go ahead and do this right here so that we can keep the schematic in view as we work today. Okay, so here I am inside my VS Code instance. Okay, so the first thing you're going to want to do to make sure that your dyad is all set up properly on your computer and whatnot is I can search on Google, JuliaHub, Dyad help. And what that will do is you'll be able to find our Dyad documentation as the first result right there. So you can go ahead and click on that. And at the very top here, there are some important or very useful links, specifically installation. So if you go here and you go to installation, it'll walk you through how to create a Julia Hub account, install Visual Studio Code, and also install the Dyad Studio extension into your VS Code. And specifically in my VS Code right now, if I go over here and I expose the extensions over here, you'll see that under my installed extensions, I have Dyad Studio, all right? And you can simply just install this from the VS Code Marketplace, okay? So that's the first thing you're gonna wanna do, just make sure you have this installation step completed. And once you have that done, you can go ahead and continue with what I'm doing right now. So you'll see here that we have, we're on the installation page right here, but there's also a set of tutorials right here. There's 4 tutorials, this one, this one, this one, and this one. So what we're doing today is we're actually walking through this tutorial right here, acausal modeling and creating components. So if you are a visual listener, you can watch along with this video. If you prefer to also have something to read and follow along, the documentation for this lesson is right here. And we'll make sure to send out the links to all of this so you don't, so you can access it easily. Okay, so anyways, once you have the installation step done, you'll be ready to proceed. Okay, so now that I have my Dyad Studio extension installed, it gives me access to all the Dyad features as well as the Dyad extension and compiler. So let's go ahead and create our component library for this RLC model. So what I'm going to do is open up my command palette inside of VS Code I'm on Windows here. The command is slightly different if you're on a Mac, but here I'm doing Control-Shift-P to open up my command palette. I'm going to type out Dyad and I'm going to select Dyad Create Component Library. Once prompted, I'm going to give my component library a name. And I'm going to just go ahead and name this RLC Components. RLC Components. And then I'll go ahead and save my component library inside of this folder on my desktop. You can feel free to save it wherever you'd like. Okay, so once you do that, once you select where to save, what's going to happen is a new VS Code instance is going to open up, and it's going to have your generated component library folder structure exposed on the left side. So you can see here we have this RLC components project folder um, in my Explorer on the left side right here. So um, what happens, what's going on with the dyad? So remember, recall earlier I was talking about one-to-one mapping between your dyad model and also Julia code, in other words, the code-based representation of the models. So what the dyad extension, in other words, the dyad compiler is doing in the background here is it looks inside of this dyad folder right here, and it looks for any models inside the dyad folder. And then it will generate the corresponding Julia code for those models. So for example, right here, we have a hello, just a, a generic model loaded in with our fresh project. It's just a model called hello. And then you can also see right over here, there's a corresponding code-based definition for what the hello model should be. Okay, so this will hopefully become a little more clear as we continue working here. But the gist is you're only going to work out of this folder right here, and then the corresponding generated files will appear in the generated folder for you. Okay, so what I'm going to do is create a new file inside of this Dyad folder right here. I'm going to right click and select new file, and I'm going to call this file rlc underscore parts dot dyad. rlc underscore parts dot dyad. And now let's go ahead and begin. So the first thing we're going to do is we're going to start with a connector. So modeling physical systems generally starts by defining connectors because connectors are used to represent the information exchange between components that are connected to each other, right? So what you see over here, we have these capacitor component, a resistor component, an inductor, but you need this little node here at the end, which is a connector. And you need to use these connectors to connect various components together. Okay? So we're going to define a connector right here called a pin. And this connector is going to have two variables, a potential variable V for voltage and a flow variable I for current. So the flow variable here is generally chosen as a variable that is a time derivative of a conserved quantity. So for example, here current is the time derivative of a charge. And then potential variables are variables that are the quantities that drive the flow, right? So for example, a difference in voltage would cause dynamics in our system. Okay? So that's how we're going to define our connector. Now let's go ahead and continue and start to define this resistor component. Okay, so let's see here. Oh yeah, and also please go ahead and ask questions or anything in the Q&A, and then I'll try to address them at the end of the webinar. Okay, if you have any questions. But okay, so let's go ahead and just define a resistor. You'll notice that when I save this file, this new pin definition appears inside my generated folder, right? Because I defined a new model inside my Dyad folder, so the compiler generates a new file for me. Okay, so you'll slowly start to see this generated folder get more populated with more files as we add in models here. So let's go ahead and define a resistor. So I'm going to go component resistor. Okay, so when we define a component, the first you can add in parameters as well as variables to the component, and also relations, or in other words, equations which dictate the behavior of these components. So here, first, my resistor is going to have two pins. We'll have a positive pin called P, as well as a negative pin. We'll call that N. The resistor itself is going to have a variable across it for a variable V for the voltage across it. And it's also going to have a variable I for the current through it. Additionally, it's going to have a parameter called R, which represents the resistance of this resistor. So far pretty straightforward, right? We're just creating a positive and a negative pin, kind of what you see here. These pins, there's also a voltage across the resistor, a current through it, and these, of course, these change over time, right? That's why these are variables. And then we have a parameter which is static and does not change over time. And this parameter simply represents the resistance of a resistor. And as you can see here, later we're going to want to set the resistance to 100 ohms. And you'll see how we do that in a sec. Well, actually, just want to mention now, you could set the default resistance to 100 ohms by just specifying it like this right here if you prefer to do it like that. Yeah. But for now, I'm just going to leave this parameter undefined, meaning we have to specify its value when we instantiate it inside of other components. It'll make more sense once we get there. Okay, so that's all we have for the variables and the parameters. Now let's define some relations or equations for this component. So for our resistor, the voltage across the resistor is equivalent to the difference in the voltage between the positive and the negative pins. Okay, that's simple. And then the current through the resistor is equivalent to the current through the positive pin. And then the sum of the current from the positive and the negative pins is equivalent to 0. And then finally, one more equation we need to add in for this resistor is, of course, the voltage current relationship for a resistor, in other words, Ohm's law. So we have V is equivalent to I times R. And that's it. So I'm going to go ahead and hit save right here. And now you can see we have a resistor definition inside our generated folder. And I'm just going to go ahead and open up this file just so we can take a look at what's inside it. Okay, so here I've opened up the resistor definition file, right? This was generated by the Dyad compiler from this model that I defined. And you can see here, it says, do not edit this file. This file was generated by the Dyad command line compiler. If you want to edit the model, what you should do is instead update the Dyad source code. And what that is referring to, it's referring to this right here. This is the Dyad source code. So you want to be working out of the Dyad source code and not the Julia files. Okay? But so down here, you can see what's kind of going on here. The Dyad compiler has created a function for us, which returns a modeling toolkit model of a resistor. And you can see here that the resistor is defined the same way that we defined it in Dyad, right? We have parameters right here. One parameter for R, which is the parameter we defined right here, of course. We also have two variables right here, V and I. That's simply the variables we defined over here. We also have these components down here, right? We have a pin called P and a pin called N, corresponds to that. And finally, at the very bottom here, we have these equations which correspond to what you see right here. Okay, so this is the one-to-one mapping we're talking about between Dyad and code-based representations. I'm going to go ahead and close this resistor underscore definition JL file now because we're not going to do anything inside of it. I just wanted to highlight this right there. So now we have the resistor. So let's go ahead and continue, right? So we've defined these positive and we've defined these pins in the form of this connector right here. And we've also defined this resistor right here. So we got a few more things to do, right? We got to do the capacitor, inductor, source, and also this ground thing. So I'm going to go ahead and define a capacitor right now. I'm going to do component capacitor. It's going to have some relations just like before. And okay, so for my capacitor, it does share some things with the resistor here. It also has a negative and positive pin, and it also has a variable for voltage and a variable for current. So what I'm going to do is I'm just going to copy this code right up here and place it into my capacitor right down here. Additionally, the first three equations for my resistor, for the voltage, the current, and the sum of the current being zero, this is also valid for my capacitor. So I'm also going to go ahead and stick this right down here. Okay? So what else am I missing for my capacitor? So just like the resistor, the capacitor is going to have its own parameter, and this parameter will be C, and it will stand for the capacitance of this capacitor. Okay? C is the capacitance of the capacitor, just like the parameter R is the resistance for the resistor. And then just like before, where we had a voltage current relationship in the resistor, we're also going to have a voltage current relationship in the capacitor. And that is going to be, of course, this equation right here, which is the capacitance times the derivative of the voltage is equivalent to the current. And okay, so before we continue with inductor and the source and the ground components, let's look at the work we've done so far. So you can see right here that the resistor and the capacitor, they actually have some similarities, right? Oh, yeah, they have a different parameter. One's resistance and one's capacitance, and also their voltage and current relationships are obviously different. But what do they share? They share, well, they both have these pins, right? They both have a positive, negative pin as well as a variable for voltage and current. And they both actually have the exact same equations for the voltage and the current um, with the pins, right? The relationship between the voltage, the current, and the pins. So they're all the same here. So how can we take advantage of this similarity to avoid redundancy or typing redundant code, right? So right up here, let's define a partial component. I'm going to design a partial component called one port. Okay? So partial components are components that are not complete on their own, but they can be used inside of other components to build a complete component. Okay? So this partial component is also going to have relations and there. Okay, so what we're trying to do here is we're trying to build a partial component one port, and we want to reduce the redundancy that you see right here. Okay, so what I'm going to do is I'm going to take the commonality of the resistor and capacitor, and I'm just going to stick it inside of one port. Okay, so I'm going to copy the the code for the pin as well as the variable V and I, and I'll go ahead and paste it into one port right there. And I will also copy the first three equations in my relations and copy and paste them inside my one port relations. Okay, so now we've defined one port like this. We can use one port to have other components take advantage of it, right? So you might be able to guess already, but you can see here now inside of a resistor, what we're going to do is we're going to get rid of this code right here. I'm going to go ahead and delete this right here, delete that right there. And then I'm also going to call this. I'm going to say my resistor extends one port. Okay? So by doing that, what that means is the resistor is going to inherit everything that one port has. So all of these variables and components, the resistor also has because it extends one port. And all the relations that my one port has, well, the resistor also has that because it extends one port. Okay? And we're going to do the exact same thing for the capacitor down here. So the capacitor will now extend one port, and we can get rid of all this redundant code. Okay, so hope that's clear what we've done so far. Created a partial component one port, and then we created a resistor as well as capacitor. The inductor is going to be very similar to the resistor and capacitor. So let's go ahead and build that up. So component inductor relations and my inductor is also going to extend one port. It's going to have its own parameter for the inductance. We'll call that L. And it's also going to have its very own voltage current relationship, which is going to be L times the derivative of the current is equivalent to the voltage, right? This is simply the current voltage relationship for an inductor. All right. So what else? Taking a look at the schematic on the right side, we've done the inductor, capacitor, and the resistor. So what we have left here is we need to define the source and also ground components. The ground component is going to be pretty straightforward here. It's simply going to have one pin that we'll call G, and the voltage across that pin will be 0 because this is a ground component. And the final thing we need to define before we can stitch everything together is this source component, right? So this is, we're calling this component a source. And what it is, what's happening under the hood is it's a step voltage. So it's a voltage source. So I'm going to call my component here, I'll call it step voltage. This also extends one port. We have a parameter VF for voltage. So the step voltage is going to give a signal of 32 volts and also a parameter step time of 5. Meaning we don't want the voltage signal to begin until 5 seconds into our simulation. Okay? So these are the parameters we defined. How are we going to make sure that this component uses these parameters the way I just described, right? Like the voltage signal needs to be 32, and I want the voltage signal to begin after a step time of 5, or a simulation time of 5. So in the relations, this is how we're going to do it. So the voltage and the step voltage is equal to, I'll go ahead and write this out, then I'll explain it. Step time. Yeah. Okay. So here, what's going on is this is going to be the voltage. This equation specifies how much voltage is coming from this step voltage component. If the current simulation time is less than the step time, in other words, if the current simulation time is less than 5, then my voltage signal will be 0. Otherwise, if the simulation time is not less than 5, then what the voltage signal will be VF. In other words, 32. Okay, so said another way, from simulation time 0 to 5, the step voltage will give out a signal of 0. And then after the simulation time of 5, this step voltage will give out a signal of 32. Okay, so now we've done it, right? We've created all the subcomponents that we need to build up our RLC circuit. We built up this pin connector, which allows us to connect these components together. We built up a partial component called one port so that we could take advantage of the inheritance and extension properties of Dyad. We built a resistor, capacitor, and inductor. These were all very straightforward. They just extended from the one port component. They all have their own parameters as well as their own current voltage relationships. And then we have a ground and step voltage component. So let's build up this RLC model now. So in the Dyad folder, I'm just going to create a new file here, and I'm going to call this file RLC underscore parts. And this is where I'll keep my RLC model. So in case you're wondering, the, you can have as many Dyad models as you like in a single Dyad file, right? So you can see here, this Dyad file has a whole bunch of things in it. So the name of this Dyad file doesn't need to correspond to any model you have in here. Okay, it's just simply how you'd like to organize your models, so it's easier for you to move around and navigate your code, right? So I simply just put all the subcomponents inside this RLC parts. And over here, whoops, I named this the wrong thing. It's supposed to be rlc.dyad. And then I'm going to put my big RLC component over here in the RLC dyad file. Okay, so how are we going to do this? Let's go ahead and give our component or RLC model, the backbone that we've been doing. So we'll just do component, give it the name RLC. We have some relations as well. Okay, so our RLC component, right? This is our entire RLC model. We're going to need to make sure that it has these individual components, meaning we need to make sure our RLC model has a capacitor, it has a resistor, an inductor, a source, and a ground component. So that's what I'll do right now. So I'm going to declare a component called resistor here, and this is going to be an instance of my resistor component that I created right over here. Right? So this is what this is calling now. It's calling my resistor component. And what I'm going to do inside of this resistor component is I'm going to supply it a keyword argument of R equals 100. So what this is doing is it's including an instance of the resistor inside of my RLC model, and it's setting the parameter R to 100. Okay? Remember earlier I said that you can also leave defaults in here. So for example, if I had a default of 99 right here for my resistor, doing something like this would simply overwrite that 99 to set it equal to 100. And if I have a default value for my resistance, I technically don't actually need to give any kind of keyword argument, and then it'll just use the default value. Okay, that's just for illustration purposes, but I'm going to go ahead and revert back to this. Okay, so great. There's our resistor. Now let's include the capacitor. Capacitor. We'll set the capacitance to 1 microfarad. This little m right here, Dyad will be able to read as micro, or sorry, 1 millifarad, not micro, milli, 1/1000th of a farad. We'll have an inductor. We'll set the inductance to 1 Henry. We'll also has a step voltage, and we'll call that source. Right? So source is just an instance of my step voltage. And you can see here, I'm not supplying any keyword arguments to the step voltage. That's because I'm happy with the default values that we specified right here. And then finally, a ground component. Okay, so great. So now our RLC model has all 5 of these components that we need to create this circuit. What we need to do now is define these connections, right? Here, we're going to have 3 connections we need to define. The first one, well, you can do it in any order, but this is one of them, the connection between the inductor and the source, the connection between the inductor, the resistor, and the capacitor, as well as the connection between the resistor, capacitor, source, and the ground. Okay? And if you look at these pins on the left and right side of these components, the darker pin is going to be taken as the positive pin, and the lighter shaded pin will be taken as the negative pin. Okay? So how do we do this? So what we're going to do is we're going to use a set of connect statements to create these connections. So what we're going to do is we're going to have 3 connect statements so we can create all these connections. So we'll start off with this one right here. Okay? So you can see here that this connection, it connects the positive pin of the source to the negative pin of the inductor. So that's what I'll specify right here. So right here, I want to connect the positive pin of the source to the negative pin of the inductor. Right? You see here that we are connecting the source's P pin, which is right. Yeah, so the source is an instance of step voltage. Step voltage extends one port, and what does one port provide? One port provides these pins, right? So that's what we're reaching into right now. We're connecting connectors with these connect statements, okay? We're connecting connectors with these connect statements. So Source.p is a connector, as well as inductor.n. That's also a connector, right? The negative pin of the inductor. So now let's do this connection right here. The inductor's positive pin, resistor's positive pin, and the capacitor's positive pin. So here I'll go inductor.p, resistor.p, and capacitor.p. And then finally, we have this connection right over here. What we're going to need to do is the capacitor's negative pin, resistor's negative pin, source's negative pin, and the ground's positive pin. So we'll go ahead and do resistor, negative pin, capacitor, negative pin, source, negative pin, and the ground's G pin, right? Because inside the ground component, we called our pin G. So that's why we're doing that. Okay, so there it is. That's simply it. This right here is the dyad equivalent of this right here. This is the dyad representation, and what you see on the right is the GUI graphical representation of this. Okay, so here, and of course, we're not actually opening up the GUI here today. Like if I were to open up the GUI and load this project, we could actually show you this instead of just a screenshot. But for today's focus, we're spending our time in the code base interface today. So let's go ahead and analyze this model and take a look at some of the voltage and current signals for our components. So let's go ahead and create an analysis to simulate this. So right down here in this same file right here, I'm going to define an analysis called sim RLC. This analysis is going to extend a transient analysis. Extends transient analysis. And we have stop. One mil. Real tall. This 1 mil. Okay. So what we have right here is we have a analysis that we've defined and we're calling it sim RLC. This analysis inherits from or extends from the transient analysis type. We're providing it a few parameters for the analysis. So we're going to simulate for 10 seconds, and we also have some absolute and relative tolerance levels for the solution. And you can see here the model that it's going to be using inside of this analysis is the RLC model that we created right up here. Okay, so now that everything's saved, and I can look inside my generated file folder to see like, oh yeah, look, here's my RLC definition, as well as my analysis definition and all the other things I created. So it looks like we're good to go. Okay, so what I'm going to do now is I'm going to go ahead and instantiate this project, this Julia project, and then we can run the analysis. Okay, so I'm going to open up my command palette again by doing Control-Shift-P, and now I'm going to start up the Julia REPL. Here inside my REPL, I'm going to enter the package manager by hitting the back or the close bracket key, and I'm going to instantiate my project. Okay, this is going to take me about 20 seconds to go. While that's going, I want to show you something over here. Just kind of walk you around the documentation a little bit, right? So here, this is the home page for our Dyad documentation. I showed you earlier that installation page is where you want to get started to install everything. If you go to tutorials, of course, we have this acausal modeling and creating components tutorial, and this is what you're following along here today. But then there's also a lot of other things in here other than just installation and tutorials. Right down here, we have the manual for a lot of the things inside of Dyad, how syntax works, components, analyses, frequently asked questions. Pardon me, I'm going to go ahead and do it using. And then we also have down here analysis libraries. So information on things like, look at transient analysis. Like what's a transient analysis, right? That's what we just extended from. So if you want to learn more about what a transient analysis is, how it works, how it's defined and this and that, you can see it in here. And then also down here, we have our component libraries right down here. Okay. So, if you're kind of curious inside this, you might be kind of curious, right? Like, okay, do I really need to define this pin and this resistor and these very, very basic components on my own? Or is there something I can leverage? So if you go in here in these component libraries down here and I click on Dyad, there's a bunch of things or types that Dyad provides or components Dyad provides. If I go to the very bottom, you actually see that we do provide a pin connector and all these other connectors. So of course, today we wanted to go through the exercise of creating it, but just know that these are already inside of Dyad, like these very basic level type components. And if I go to electrical components right here, this is the electrical components library, you can also see that, hey, there's a definition for a capacitor and a ground and a resistor and so on. Oh, and an inductor right here, right? So all of these can be used, and you don't necessarily need to build everything from scratch all the time. Of course, for today's lesson, we wanted to build from scratch so you can see how it works. If you want to see how you can use these components that you see right here to create an RLC circuit rather than doing it from scratch like we just did, I recommend you go to the Getting Started section. If you go to the Getting Started, at the bottom of this, it shows you how to build a RLC circuit using components from our standard libraries. Okay, just wanted to give you a quick preview of what's going on in our docs, but right over here, let's go ahead and run the analysis. So now that my project is brought into scope, I'm gonna just carry out the analysis. So I'm gonna do, oops, sim RLC. So result is equal to sim RLC. That will carry out the analysis that we defined. What happened here? Did I define something wrong here? Let me see. Just a second. Let me make sure I did all this code correctly. Might have did a typo as I was. Oh, I know what I did wrong. I forgot to, it says right here, initialization is underdetermined. So I needed to give an initial condition to my resistor. So over here or to my RLC circuit. So over here, under the relations, I'm going to go ahead and define an initial condition for the current across the inductor or through the inductor, and I'll set that to 0. And also give an initial condition for the voltage across the capacitor, and I'll set that to 10. All right, so the reason why that errored out was because it needed an initial condition for it. Okay, so this should be good now. Okay, great. Yeah, so I was just missing the initial conditions when I set that up. Okay, so now that our analysis is done, we have everything stored inside the result variable. Let's go ahead and plot the result. So I'm going to bring in the plots package by doing a using plots command in the Julia REPL right here, and I'll plot my result. And there we have it. So right here, We have a plot of our simulation, which ran for 10 seconds, right? We can see the voltage across our capacitor throughout the 10 seconds. Of course, we see the voltage across the capacitor begin at a value of 10, which makes sense because that's the initial condition we provided. We also see the current across or through the inductor begins at a value of 0. That's how we initiated it. And we also see the current throughout the rest of the simulation. So let's say, okay, so let's say you're like, okay, well, I see that we can see the voltage for the capacitor and current for the inductor, but what if I want to plot like some other signals for my system? What if I want to know what the current is throughout the capacitor, resistor, and source and inductor and whatnot? Like, how do I plot specifically what I want? Right, so I do want to show you how to do that real quick. So you can bring in Dyad interface and you can use the artifacts function to pull out the simplified system from the result. And when you pull out the simplified system, it allows you to index into the plotting function. Okay, so I'll show you what that means right now. Right, so I did model is equal to artifacts, this and that. So I pulled out the simplified system and stored it inside model. And now with the plotting command, instead of just doing plot result, I'm going to plot the result, but I'm going to tell it specifically what to plot. So I want it to go into my model, right? This is the same variable that we pulled right here. It's a symbolic variable in this case, but I want to plot the capacitor's current, the resistor's current, and the inductor's current. And there you have it. So now, instead of just plotting the default variables that the system wanted to plot, we specified, hey, like please plot the capacitor's current, resistor's current, inductor's current, and that's what we get here on this plot. Okay, so that's it. Back to here. So in summary, what we did, the problem at hand was to design this RLC circuit inside of Dyad and then provide a voltage source to it to see the system's response. What we did was we went into Dyad, we created this one port component to reduce redundancy. Then we defined resistor, capacitor, inductor using that one port component. And then we define the RLC component, simply taking advantage or using all the components we defined, a initial condition for the RLC, and we connected all of the components together. And then we ran an analysis. And of course, this is the simulation results we got. We saw the standard plotting function, plot the voltage across capacitor and current through the inductor. And then we also showed you how we can plot the specific signals we want on the right side right here. Here are a bunch of Dyad resources that are very useful. We'll make sure to send out these set of slides as a follow-up email, so you don't need to worry about remembering what you see right now. But this is simply a link to our home webpage, the installation page I showed you, the getting started tutorial. Generally speaking, you should probably start with this getting started tutorial. It walks through some fundamentals of Dyad. Here's the RLC tutorial that we did today, what we just did right now. And here's some links to some useful webinars. So this link right here is our very own Dr. Michael Tiller. Talks about Dyad Studio, its design, and the philosophy behind it. This link gives you access to the upcoming webinars we have, and also this allows you to access past webinars we've had. I do want to click on this one really quickly, this past webinar one. And if you go into that past webinar one, and I scroll down just a little bit, this one right here. On March 4th, I did a webinar called Building Dynamic Models Using Bidirectional Graphics and Code. So this webinar is the webinar that shows you how we can manipulate this model using both the GUI and the code-based interface. So if you kind of want to see that in action, check out that webinar. And that's it. So in summary, today what we did was we went over brief overviews of Julia programming language and Dyad. And then, of course, we spent the bulk of our time modeling, simulating, and analyzing our RLC circuit. That concludes everything for today. If you have any questions at all, please reach out either to JuliaHub or to me. My contact info is right here, and we'd be happy to have any conversations, answer any questions that you like. And that's it. I will hang around for a few more minutes to answer any questions, and I'll go ahead and take a look at the Q&A right now. How amenable is Dyad to stochastic inputs and inputs derived from other models, for example, CSV text and CDF, along the lines of a small Goldson model? So, anonymous attendee, unfortunately, I am not equipped to answer this question, but what I'm going to do is I'm going to ask this question to people who are smarter than me. And well, I don't know who sent this question, so I can't. Well, I'll send. We'll try to send up this question just in the follow-up email to everyone. Yeah, but I don't know the answer to this question, so yeah, sorry about that. But thank you for asking a question, though. Okay, if there's nothing, no other questions, no other comments, Jasmine, I think we can go ahead and wrap it up right there.
Yeah, sure. Thank you for the session.
Thanks, everyone. Have a good day.
Thanks, everyone.